It's not less
You okay like that? Sure? Okay. I don't know what's going on with the desks in here. It seems like every day is a different configuration. But, all right, everyone, let's do it. It's 11 o'clock. We need to finish up partial fractions. And I haven't shown you all the different varieties of things that we can see. But I did ask you to bring your graphing calculators. Did you happen to? Yes? Also, I want to mention that I'm not feeling that great today. Not feeling that hot today. And so I'm going to be in my office hours right after class, but I don't know if I'm going to hang the whole time, just because I'm feeling a little. I have to give some makeup quizzes for some other students. I don't know if I'll make it the whole way. We'll see. We'll see how things go. You ready? Okay. All right. Did you hear what I just said? Because it impacts you. No? I'm not going to be in my office hours potentially for the whole time today. So I don't want you to show up and I'm not there because I'm not feeling well.
Okay.
Okay?
Yes, sir.
All right. So I may be there. I might just, I don't know how it's going to go for me. So, yeah. So I just want you all to know. All right. So here we go. Your calculators, have them ready. We will draw on them when it's time. We're going to start this new problem. It's a rational function inside the integral, right? Polynomial divided by a polynomial. I also maybe would think about a u sub because this is cubed and that's squared, so maybe, but it's not going to work. Because if you let u be the bottom, what's the derivative of the bottom? 3x squared plus 4, and you could probably make that a 3x squared, but see, this is an x term, and you don't have an x term in the derivative of the bottom. So let's just go straight to partial fractions. All right, so for partial fractions, the first thing I do is I look at the degree of the numerator and degree of denominator, and I'm going to use long division if this number up here is bigger than or equal to this number, but it's not. Right? So I don't need long division. So if I don't need long division, I now do what? Completely factor the denominator. You don't need to factor the numerator, only the denominator. So I'm going to take my integral here. On the bottom, can you factor that at all? Yeah, you can just pull a GCF out, right? Greatest common factor. All you can do is pull an x out. You'll be left with x squared plus 4. And that's it, right? You cannot factor x squared plus 4. There's no formula for that, right? No. If it was a minus, then yes, you could do plus 2 minus 2, x plus 2. Not for the sum of squares, no. There's not one. Only for the difference.
No, there's one for
cubes. Sum of cubes. Not for sum of squares, though.
But that's x squared plus 4, which is 2 squares.
I understand that, but there is no formula for factoring that. A sum you can't factor. If it's minus, you can. Okay? Trust me, it doesn't factor. All right, so we're here. This doesn't factor anymore. So now if we're going to do partial fraction decomposition, we have to identify what are these factors in the denominator. What are they? So the first factor, x, is linear, right? That's linear. And the other factor, x squared plus 4, is an irreducible quadratic, or in other words, a non-factorable quadratic. So I'm going to put IRR for irreducible quadratic. Irreducible quadratic. That dictates what my partial fraction decomposition is going to look like. So now let me do the partial fraction decomposition over here. So I'm not doing the integral right now. I'll come back to that when I finish this. I just keep on having this feeling like I want to sneeze. It sucks. Okay. So for every linear factor I have, I need to put like a over that linear factor, b or c. But I only have one linear factor, so I'm just going to put an a on top of x. And I'm done with that. Or that. What do we do for a quadratic? That's irreducible. What do we do? Yeah, we put a linear expression on top. We put bx plus c on top of that quadratic that's irreducible. Why? Because that's the method, okay? That's what works. That's what will help us do the partial fraction decomposition. All right, now we go ahead and proceed with the method. So I'm going to clear fractions first by multiplying both sides of this by x times x squared plus 4. So I multiply this side times x squared plus 4, and I multiply everything over here by x times x squared plus 4. On the left side, everything goes away except the numerator. And on the right side, distribute here. If I distribute there, here to here, the x's go away, right? I still have the a, and I still have the x squared plus 4 in parentheses. So I'm going to write that. A x squared plus 4, x squared plus 4. And then when I distribute here to here, be careful. What goes away on that distribution? The x squared plus 4. So I still have the x, right? And I still have the bx plus c. So I have to write it this way. Bx plus c times x. I will maybe on the next line. It just depends. But that's what I have when I distribute, right? Initially. Any questions up to that point? Any questions as to why I used a over x and why I did bx plus c over? We're okay?
I have a question about
Yes.
that. Why?
That's what works for partial fractions. I mean, that's the method. The method says anytime we have a linear, we put a constant on top. Anytime we have an irreducible quadratic, we put a linear expression on top.
Would it be good practice to have c be the constant
To have c be the what?
over the constant or anything like that? Because I mean, there's plus 4, so it's over the plus 4, so it's just like, constant c.
I'm not following you.
Okay, gotcha.
Yeah.
A over x, right? That's
Yes.
a
Constant over linear.
A over a variable, and then bx over x squared. So that's
Oh, you mean like split it into two?
well, but it's not splitting it. But no. Once you get to the c part, that's if you separate that fraction, it's like c over plus c over 4.
Yeah.
So and that's a constant.
Mhm.
So would it be easier to just just put
The method, look, we're not going to change what partial fractions is the way it's like presented. The method is that if this is irreducible in quadratic, you put a linear expression on top.
okay?
If you want to do some adaptation of that, as long as it's correct, you could do it, but that's the method we're going to stick with.
So irreducible over quadratic.
No.
No. How did you say it again?
Linear expression over an irreducible quadratic. Okay, so while we were just having this dialogue, everyone else was thinking about what we do next?
Yeah,
What do we do next?
you can solve for A, but not B and C.
Yeah, so our goal is to figure out, can we find A, B, and C? If I can hear you, everyone can hear you. That's all. Okay. A, B, and C, we need to figure out what they are. So the method we did last time was, can we figure out maybe just what A is? And what do y'all think? We can? How?
Plug in 0.
Plug in 0 for x. Because if you plug 0 in for x here, it'll kill everything here, but it doesn't kill this, right? So I'm just going to first try this short way of getting something at least. So I'm going to let x be 0. And if I do that, I replace everything. This whole equation, all the x's get replaced with 0. The left side becomes 4, and the right side becomes a times 0 plus 4, and then plus all of that becomes 0. That will allow me to solve for a at least, right? What will a be here? 1, right? So this is 4 times a, so 4 equals 4a, and a is 1. Okay, I know what a is. The problem is, it's not as easy to get b or c, because to get b, you're going to have to kill this off, right? And that's impossible to kill off, because there's no value of x that you can plug in here that's ever going to make this 0 unless you bring in imaginary numbers, which we are not messing with imaginary numbers in here. So there's no real number that can make this go away. And same for C. I can't get C because I can't kill that off. So that forces us to go to the long method. But at least we know A is 1, right? Which might be helpful later. So now, the long way means you have to actually expand all this out. So I'm going to go back up to this original expression here. And I'm just going to, now, do y'all want to replace A with 1, or do y'all want to multiply it through, like, just leave it as A? Because I know A is 1. Do you want me to replace that with 1, or do you want me to just push an A through?
Probably the 1.
Replace?
Yeah.
Okay, I'm going to replace that with a 1, which makes that what? X squared plus 4. And then over here, the only thing we can do is multiply this x through, so we get plus bx squared plus cx. Yes?
I know that last time we did grouping, but a lot of that was off.
A lot of
Is
that
that
kills
a
off.
way to do it instead of,
Like moving things around right now?
yeah, like the 4s you can cancel.
You can do
out.
that, yeah, sure. If you wanted to, you could start simplifying this right now.
Okay.
Yeah.
I tried that, but no, it's stuck.
Okay, well, we can continue with what you have.
Okay.
Yes?
How would you simplify it?
Well, I've got it. Simplify. I'm not trying to simplify. I'm trying to find B and C. So I'm going to try and manipulate this and create 2 equations. So let me work through it, and you'll see. Hopefully. All right. Everyone good up to this step, though? Yes. Oh, I saw your hand. Yeah. Sorry about that.
So you said our 2 options was either to just replace A with what it is, or to distribute A through.
Yes.
Like, why are those the 2 different options?
Well, we can say, since we know what A is, right, we can actually just replace it now. Or we can just work with this thing arbitrarily, acting like we don't know what A is, and then figure out what happens, and then later on plug in A as 1.
So if A were something like more complex, it would be better just to distribute it through and then deal with it later?
Probably. Like if A was a fraction, I probably wouldn't want to mess with it.
Oh, okay.
Okay, so I'm here. What's being suggested here is like, let's just work with this a little bit right now, like subtract x squared. I think that's what's being suggested. And subtract 4 on both sides.
Yes.
If you do that, then you get over here x squared minus x equals over here, what's left? Bx squared plus cx. Right?
And then I pulled out an x and divided by x.
Okay, so that's where, this is the point at which you don't have to do any more factoring. Because what you're trying to do is figure out what b and c are that makes this true. But b is the coefficient of x squared, right? And what's the coefficient of x squared here? 1. So that would have to match, wouldn't it, for these to be equal? This side, this and this would have to be the same. So basically that tells you that b has to be 1. And then also, right here, this is what? C has to be the number in front there, which is a negative in front of there. So from just that, we can tell that b is 1 and c is negative 1. We're just matching coefficients. Yes?
Is that just something fundamental about, it's kind of hard to find the words for it, but when you have an equation with 2 sides that have the like matching, they're both polynomials and they have the same amount of degrees?
Then coefficients must match.
Oh, okay.
Exactly. Which is a little odd that that's the case, but
Yeah.
it does, in order to maintain equality, the coefficients on each power of x has to match exactly.
Match power.
Coefficients. These coefficients must be the same, and those coefficients must be the same if we want to say that they're equal.
I mean, no, but that's just fundamental.
Yeah, that's what I'm saying. That's what we're saying. It's a fundamental principle of it. All right, I'm ready to get back to the problem. Oh, shit, I just erased it here. My original integral can now be broken down to be a over x, but we said a was 1, right? So 1 over x, and then we have plus, all right, b for us was 1, right? And c was negative 1. So this is going to be 1, and that's going to be negative 1. So 1 in front of x minus 1 over x squared plus 4 dx. That's where we are. And I look at those, and I don't like writing a 1 in front of x. So I look at that, and at least the first integral, I'm not, I'm okay with this. This is just natural log. So I'm going to say natural log, absolute value of x. That's the answer to the first one. And then I split it up. Now I still have to do the antiderivative of this. And what are you looking at here? What do you see in this particular case?
Isn't that the trig?
You might be able to go trig sub here. But just look, what's up here? What is this?
The derivative of the bottom.
Okay, but what is it? It's polynomial, but what type of polynomial? Linear, and down here? Irreducible quadratic, right? So what was the technique for linear over irreducible quadratic? Oh, sorry, and you're missing the x term, right? There's no x term in here. So I heard split up. Could we split?
Yeah.
You could split it.
Oh, yeah, that's true.
You could do x over this, 1 over that. You could do that. Yeah. Oh, yeah. There's 2 terms on top of one thing. I'm going to treat this as one big thing. So I could. This is nothing wrong with this. You can go x over that. And then let's say minus, because this was a minus 1. So minus, and then over here I'm put 1 over x squared plus 4. Dx.
Probably a very basic fact in all of that, let's say.
Yes, it is.
So, I have a question.
Yes.
Would you say, as a general rule of thumb, it ever really hurts to just constantly break down fractions whenever you can into 2 integrals? Or will that
I wouldn't say that anytime I have something like this, I'm just going to start doing like this over this, this over this. Generally, I wouldn't. Like in the original problem, we could have done that, right? Like this over this, this over this, this over this, but that wouldn't have helped us. Like it wouldn't have made things easier for us. So I'm not going to say, you said general rule of thumb.
Yeah.
No, not a general rule of
On the
thumb.
flip of that, then should we always avoid doing that if at all possible?
I think you need to see and understand what's in front of you. Like that's the thing. Because here, why do we split this one? Like why did you split this? I don't know who said split.
You could do a U sub on that, and then that one is just like the inverse tangent.
Yeah, so see, it's how far ahead are you seeing that this split will become a basic U sub,
So each one's just.
and then this one right here is just a formula 17.
Quick question, could you look at U sub and split it up?
Yes, you could have. You could have done a U sub here as well. But I think this way is a little more efficient.
That's going to turn into a natural log, right?
No, this is formula 17. Right? Because you got,
Formula
so
17?
this one is. This one is basic U sub. Let's finish the problem up. All right, so here's where we are. We have natural log absolute value of x. That's the first one. Plus, all right, this right here, I'm going to do very quickly. This would be a U sub. U would be the x squared plus 4 in the denominator. Trying not to sneeze. The derivative of that would be 2x dx, which we have x dx, right? So we'd have to scale by 2. And then that integral can be rewritten how? How would this integral be rewritten if you did that substitution? 1/2, I'll pull it out front. 1 over u du. So that one will become a natural log, right? But with a 1/2. So the antiderivative would be the 1/2. And then it was natural log. What was the u for us? X squared plus 4. Well, that's not x squared plus 4. And then plus, now I have to do, oh no, minus, sorry. Minus, now I need to do this. And that's formula 17, right? And formula 17 says you have to figure out what a is. A for us in that formula would be what? 2. And so it's 1 over a inverse tangent of x over a. So 1 over 2 inverse tangent of x over 2 plus some constant.
separately. Is it because of the du?
Yeah, because if you try u sub here, right, where's the derivative of that?
We can't. You can't back on the
You can't, okay, so you know when I've done that magic on the outside, it's always been a number over a number, right? You cannot come in with a variable over variable. You can't do like x over x and then push it in, because then you've actually changed the problem because you don't have control over x. It's constants can come out of integrals, constants can go in, variables cannot come out and go inside integrals.
I'm just going to memorize it.
Yes?
In all of these integral formulas, are A, B, and C always the same? So if you're going down the problem, you're solving it, and you're like, oh, this formula also applies to this, more complete part of the problem, like, will A, B, and C still be the same?
What A, B, and C are you talking about? Like in Formula 17, the A, B, and C?
Yeah, like in Formula 17, the A, B, and C.
Are they always the same?
Yeah.
Well, if I change that problem to 1 over x squared plus 9, then A would have been 3. I'm not sure if I understand your question again.
I think I have a fun the math.
Get with me. We can talk about it. If you're not quite sure, yes.
I had a question about the second integral. It was 1 over x squared plus 4.
Uh-huh. The second one was x over x squared plus 4. The third one was 1 over x squared plus 4.
Oh, then the third one.
Okay.
I guess why I'm asking this is because it's kind of hard to remember what like I've known in the past and what like I'm learning now. It's kind of like being mixed in. But without that formula, like would that pretty much be unsolvable?
No, trig sub would have worked. But we would have had to have rewritten it as the square root of x squared plus 4 squared.
So you would get the same answer.
Yeah, you would have, actually that's how you can derive the formula. If you did this, what the hell? Yeah, what was it? 4x squared. If you would have done that, that's the original problem, right? Because if you square root, it goes away. And then do trig sub here, you would get the same answer we got. But trust me, on a test, you don't want to spend the 10, 15 minutes that's going to take. You need that time for other things. So, yes.
So how we split it up,
Mhm.
since you said that like it was linear, does it matter if it's linear? Or if it's like a quadratic, can I still split it up or like?
If you had a quadratic on the top and the bottom, you'd probably want to do long division first,
Okay.
right?
Like, okay, yeah.
You would have been back at the beginning. Like, look at this one,
Yeah.
right?
Okay, yeah.
Right? So here we have a quadratic on the top, quadratic on the bottom. So do we split it up right now? I don't know if this is what you're talking about, but
Yeah,
this is
yeah.
an example, yeah.
Okay, thanks.
So I look at that and I'm like, okay, that's a rational function. The powers are the same. So I'm going to start with long division. All right, that's what I'm going to start with. And for long division, just remember which one goes in the box, which one doesn't, right? And now I just play the game, right? Where I say, what do I multiply that by to get that? 1. Okay, and then just 1 times all of those gives me 4x squared, right? 1 times that minus 4x. 1 times that gives me 3. Also, notice I didn't have to put any zeros in the long division, right? Because every power of x was represented. Critical step, subtract, right? Subtract. Excuse me, I'm just going to grab one of these red ones over here. There's not a shortage of markers in this room. They're all over the place. Half of them don't work. All right, there, there, and there. Changing all the signs and adding down should just get x minus 1. Right, x minus 1. Now you say, okay, can you turn 4x squared into x? No, right? Not without using some sort of fraction. So I'm done. So this is going to be my remainder. So I say the original integral turns into 1, and then plus the remainder over the divisor, and the divisor is this. Questions on that? Long division?
So,
So you do have a question?
yeah, I do have a question. Did they ever, it's not relevant to the class.
Okay. All right, so we continue. This I can integrate. X. All right, plus, now I still have to find the antiderivative of this. So I'm going to look at this. And what I see here is a linear over a quadratic. I'm not quite sure if this is reducible or not. Maybe I can factor it.
I think it is.
Does it factor? Let's see. Let's do that over here. Can we factor 4x squared minus 4x plus 3 into 2 linear factors? So now go. You basically need two numbers that multiply to be 12, right? These two numbers together, they need to multiply to be 12 and add up to be negative 4. So 6 and 2 work. You would have to do like negative 6 and positive 2, but they don't multiply to be positive 12. They add up to be negative 4, but not positive 12 when you multiply them. So you play with this all day long, you're not going to be able to factor it. Okay? Now, if it factors, that's the way you want to go. Because let's just imagine that factored. Then you would do partial fractions and you would do a over the first factor, b over the second factor, and those would be nice, easy integrals because it would just be natural logs. But it doesn't factor. Yes?
So kind of like a rule of thumb right here, like in this beginning part, before you get to your actual partial fraction composition, you want to factor as much as you can. But then like him, where you got to after that, then you kind of don't want to factor too much because that's
Well, we were doing something else. When we were when we were in the middle of partial fractions, we were trying to get the left and right hand sides to look the same so that we can match coefficients. And if he would have factored, then they wouldn't look the same anymore. So, I mean, could you have factored? Yes, but does it help you get to where you want to go? No. So that's why we didn't factor there. I think I know what you're asking me. Yeah. Because you wanted to, right? You wanted to factor, remember that? When we were trying to solve for B and C, and you're like, hey, let's factor the right-hand side. We didn't do that because I was like, no, look, the coefficients doesn't match, right? Okay, yes?
So on this path, when the numerator and the denominator's degree are both equal, we do long division. Once we have our new integral, do we simplify both the numerator and the denominator, or factor out both the numerator and the denominator as much as we can?
You don't need to worry about the numerator as much as the denominator.
Okay.
Because the denominator is going to dictate what the partial fractions are going to be. Split it how? Oh, okay, yeah. So do you all want to do x over this, 1 over this?
Yeah.
You can. You can, but it's not going to be a basic u sub. It's not going to be the basic u sub. Because this u, the derivative of that is going to be a little more complicated than that. And now 1 over this, 1 over an irreducible quadratic, we know how to do that.
It's already
2 classes ago.
isn't it?
Is it?
Because we're off by a constant, because the derivative of that is 4x minus 4. Factor out 4 and you get x minus 1.
Oh, wait, that's more than constant.
you could just put right.
So, is it?
Yeah.
Is it a basic u sub?
Well,
Because the constant goes away.
Okay, whatever gets us the answer fast.
Look, if we did basic u, I think you're saying make the denominator our u. Right, it's off by a little bit. So the derivative of that would be 8x minus 4, right? Dx. And that's not that, right? You could pull out a 4, but then you'd have 2x minus 1, not x minus 1.
That's off by a constant.
Okay, so y'all have great questions, okay? But I'm like one sentence away from explaining how we approach this, all right? Okay, hold on. We started this section and I said, here are the things we need to know how to do before we start partial fraction decomposition, right? And we spent the entire day going through all these problems. At the beginning of the section, you go look in your notes. And one of the things we looked at was, what do you do when you have a linear expression over an irreducible quadratic? That's exactly what we have here, right? And this has an x term in it. And this is the one where I said, I like to do it a certain way. Tutors might do it a different way, right? See, there's a reason I showed you all that. And I even told you when we did it that our goal later is going to be able to get our problems to something like on that list of things we learned to do. So I'm there. I'm in a linear over an irreducible quadratic. I'm ready. Hand? Who raised their hand? Someone?
I did.
Oh.
So what was the formula thing? Was it A plus BX plus C? Oh, we've done this one.
Look in your notes.
How far back
A
was
squared
it?
plus B squared plus C
You have
squared?
to do the 8 over 8, and then you have
So we are gonna do the USA, but
So it's a chain rule.
we're gonna do 8 over 8 on the outside.
2 classes ago,
This way.
I started this off. 2 classes ago.
Are you checking on the first square?
2 classes ago, I said, hey, let's go through these. Let's make sure we know how to do this, right?
I was absent for that.
And then we got to this one right here, linear over an irreducible quadratic. That is exactly the problem we have right here, okay? Look in your notes and see how we did it. This was the one where I did a U sub, but things didn't look the way I wanted them to, so I forced them to happen, right? No? There's a video, right?
Yes, I like the only solutions.
Look,
You're right. I'm sure.